Okay, good day. This is Honors Algebra 2. I'm Mr. McCulley, and this is the presentation for Section 8-4, Rational Functions, Part 2. Hopefully, this one will be a skosh shorter than the last one. The notes are all the same from the last section. I just want to hit a couple high topic things that you're going to run into as you do some of these more challenging examples of rational functions. I do want to talk domain and range, same, get divisions by zero, have to remove from the domain. That's not going to change. We'll have some vertical asymptotes when you find the non-reducible factors. We'll have holes when we find reducible factors. And again, what's the difference between a reducible factor and a non-reducible factor? If I have a rational function like this, where I have the f of x and I factor the two quadratics, both on the numerator and in the denominator, you'll notice that in the denominator here, I have two factors. I have x plus 2 and I have x plus 3. The x plus 3's here, they cancel, so we will have a whole at x equals -3, because -3 will make that equal to 0. And we will have a vertical asymptote at x equals -2, because -2 makes that one equal to 0, and it will pass through the x-axis at x equals +2. So we'll have a 0 at x equals +2, because +2 will make that 0. Let's pull up our graphing calculator, and we can go to our y equals. We can clear this stuff out. We can go alpha y equals, hit the fraction button there, and we'll go, it was x minus 2, x plus 3 on the top, and then x plus 2, x plus 3 on the bottom. So zoom 6 gives me a standard window, and we can see at -2, we have that vertical asymptote. We can see at +2, we have that 0. All right, but to see where we're going to have that hole at x equals -3, we have to look at our table. So let's go to table here, and let's enter, let's go -4, -3, -2, -1, 0. And so at -3, because there's still a division by 0, we have an error there, and that's where the hole is going to be. And at x equals -2, we have an error because it's a division by 0, but because it's a non-reducible division by 0, it ends up giving us the vertical asymptote for that one. All right. Finding horizontal asymptotes, again, if the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. If the degree of the numerator is equal to the degree of the denominator, we get the ratio of the two leading coefficients, and we'll have an example of that. And if the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is 0. Today we're going to talk about a slant asymptote, and so that only happens if the degree of the numerator is exactly 1 more than the degree of the denominator. And what we'll do is we'll find that slant asymptote by dividing the numerator and the denominator, and we'll just get, we don't care, once we get to a remainder, we're just going to throw that out. And the result is just going to be a linear equation that we'll graph, and it's not a whole lot more challenging. It's just an extra step. We'll go over these steps. We'll go over the steps as we go through our examples here. So here's our first example, and I call this a medium example. And my suggestion is always going to be to try and factor both the numerator and the denominator. And so when I ask myself two factors of -12 that add up to -4, it's fairly easy. It's x minus 6 and then x plus 2. -6 times +2 gives me the -12, and then x times -6 is -6x, and then x times 2 is +2x, with the -6x gives me the -4x there. And then this is clearly a difference of squares, so x plus 2 x minus 2. And so we could have something similar to what we had in that last example where I was trying to illustrate the difference between a whole and a vertical asymptote. So when we look at this thing, I'm going to have a vertical asymptote at x equals, well, my x plus 2 and my x plus 2 cancel out. So there's going to be a hole there, and we'll talk about that. But this x minus 2 does not cancel out with anything in the numerator. So what we'll say is that at x equals 2, we'll have a vertical asymptote. We'll have a hole at x equals negative 2, because that's where we still have a division by 0. And then we'll have a 0 at x equals 6, because x equals 6 makes the numerator 0. And then a horizontal asymptote. We look at the degrees. The degrees are both 2, so the ratio of the leading coefficients is going to be 1 over 1, which will give me the horizontal asymptote of y equal to 1. So when I go to graph this thing, it should be fairly easy for us to do. I don't like that particular line, so when I grab a line and put that in there like this, let's see here, we need x equals 6. I got too many r's in my 0, so let's fix that. Sorry there, folks. I should do a good job of spelling things. All right, so a hole at x equals negative 2, so let's put negative 2 there. Let's label our y-axis. Let's label our x-axis. 1, 2, 3, 4, 5, 6. I want to put a 6 there because I know I've got a y-intercept there. I've got a vertical asymptote at x equals 2, like that, and a horizontal asymptote at y equals 1. And so let's take a look here. If I plug in, let's find our y-intercept. If I plug in 0 for x, if I plug in 0 for x, I got negative 6 times positive 2 on the top, and I've got 2 times negative 2 on the bottom. So I'll have negative 12 over negative 4, which gives me positive 3. So it looks like at y equals, so I had 1 there, let's go 2, 3, right there. So what that tells me is that because I have two choices, I can either start here below my horizontal asymptote and then come down and through and go down there. That would be wrong because clearly we have a y-intercept at 3 and the only x-intercept is at 6. So since there's no other x-intercepts, it can't go through there and go down. So it has to come along my horizontal asymptote and then go up along the vertical asymptote there. And then again, clearly it's going to, and we could test the point. So let's say I chose negative 4 or positive 4. Positive 4 makes that negative, positive 4 makes that positive, positive 4 makes that positive, positive 4 makes that positive. So I have one negative and 1, 2, 3 positives. I have an odd number of negatives. So along this interval, all of the values will be negative. And then after I go through the x-intercept, it will follow along like that. And then the only other thing that I have to add and make sure, because we did say that we have a hole at x equals negative 2, what we're going to do is we're going to, at negative 2 here, we're just going to clear that up and we'll put a little hole there right at negative 2 and connect those dots like that. And we'll call that the answer. And if you want, you can check that, but I'm going to keep moving. You type this in the graphing calculator, or you can type that in the graphing calculator and you'll get the right answer. Okay, so example with a slant asymptote. Again, I have a fourth degree polynomial and a third degree polynomial, so we've got a little bit of a mess here. And so first thing I want to factor this, and even though it's a fourth degree polynomial, it is in quadratic form. And so I need two factors of -12 that add up to -1. And so I can go x squared, and then it'll be -4, and then x squared plus 3. And then I'll get my -12, my -1, or, yeah, when I multiply that out. And then this thing here, this is a difference of cubes. So I've got a third degree polynomial and 20. So that's a special case factoring. So I'm going to come over here on the side, and we'll make this small, and I'm going to say recall. And it's been a while, I know, we've done it, but a to the third minus b to the third is equal to a minus b times a squared plus ab plus b squared. That's a factoring form that we know. So this thing is going to be x plus, or excuse me, it'll be x minus 3, x minus 3, and then it'll be x squared plus 3x plus 3 squared, which is 9. This thing is unfactorable because of the form, so that's the lowest I can do with that. Now the only other thing that I can do here, as far as factoring goes, I can go x plus 2, I can go x minus 2, and then I can go x squared plus 3, and then I have my x minus 3, and I have my x squared plus 3x plus 9. All right, so I have nothing that cancels out. And so the only 0 in the denominator is going to give me a vertical asymptote at x equals 3. And then I have zeros. All right, I have a 0 wherever this thing is 0. So, or any of the factors in the numerator is 0. Let's be clear. So I'm only going to have a 0 wherever a factor in the numerator is going to be 0. So at x equals -2, and then at x equals +2, and since x squared plus 3 is never going to be 0, there would be imaginary. So if you set this thing equal to 0, you'd subtract 3 from both sides, you get -3, and then take the square root, so you get the plus or minus the square root of -3, which is imaginary, so I don't have to worry about that. I don't have a horizontal asymptote. And the reason I don't have a horizontal asymptote is because the degree of the numerator is bigger than the degree of the denominator. So I do end up with this slant asymptote because the degree of the numerator, 4, is 1 more than the degree of the denominator, 3. So what we're going to do is we're going to do a division. We're just going to divide. So I'm going to go x squared minus 27, and I'm going to, or x to the third, excuse me, divided into x to the fourth, and I'm going to put in some placeholders. You have to remember, plus 0x to the third minus x squared minus 12. Oops, I forgot a placeholder. So it'll be minus 0x and then minus 12, and we can make it plus, it doesn't matter. But the good news is there isn't going to be a whole lot of division going on, even though this looks fairly long, because when I ask myself what times x to the third is x to the fourth, I get x. All right, well that's okay. So I can go x times x to the third will give me x to the fourth, and then x times -27 will give me -27x. All right, when I do that division, when I do that subtraction here, I end up with x to the fourth, that cancels. And then I get 0x. I've got -x squared. I've got positive 27x, and then I've got -12. Now here's the thing. Because this, in this particular case, and I have a bunch of zeros, because this is x to the third, and this is x squared, since the degree of what's left is less than the degree of the divisor, this is all remainder. And so if we go back to the notes where it says For a slant asymptote, if the degree of the numerator is exactly one more than the degree of the denominator, find the slant asymptote by dividing the numerator and denominator and disregard the remainder. So our slant asymptote is just going to be y equals what is ever here. We don't have to worry about this. We disregard it. It's just y equals x. That's it. All right. And so we know a lot about what the graph of this thing is going to look like, and we can actually go through and set up all of the pieces to it. But before we do, we should find our y-intercept. And finding the y-intercept, again, is always going to be easy. We let x equal to 0, and when x is 0, x to the fourth is 0, x squared is 0, and x to the third is 0. So we're left with negative 12 over negative 27. And what that does, and again, you can take a 3 out of each of those, and negative divided by negative is positive, so you get 4 over 9. So we'll put 4 over 9 here. I think we get enough to get graphing, so let's go 1, 2, 3, 4, 5 here on my x-axis. Let's go 1, 2, 3, 4, 5 here on my y-axis. That's a 5. We'll do a better job. Okay, you know what? We'll erase it. We'll do a better job. And then we'll go 1, 2, 3, 4, negative 5. And so my vertical asymptote is at 3, so come over here to 3, and we'll put a vertical asymptote in. And then our zeros are at negative 2 and positive 2, so there's negative 2, there's positive 2. Our slant asymptote is y equals x, so when x equals 0, y equals 0. When x equals 1, y equals 1. When x equals 2, y equals 2. And so there's our slant asymptote, and it's gonna, I apologize for this, but it's gonna kind of get in a little bit of a mess here. So what's the graph got to look like? Well, I have this y-intercept at negative, or at positive 4/9, which is almost a half, so we'll put that there. So we kind of know what this graph has to look like. It has to hug the slant asymptote, and since it's going to go through the x-axis right there, we're going to put it above the slant asymptote. We're going to hit that x-intercept there. We're going to hit the y-intercept there. Now, again, normally it doesn't cross the asymptotes, but that only applies when we're talking about extreme values. So when we're near the origin, you can actually cross your asymptotes. And so it's going to cross the asymptote, it's going to hit this 0, it's going to go through, and then it's going to go down. All right, so how do I do from 3 on? So from 3 on, there's two choices. You can either come down from the top and then hug that slant asymptote that way, or it can come up from the bottom and then hug the slant asymptote as we go through. Now, we don't have to do any work to make that decision because we've already found all of the zeros. If it were to come up through from the bottom, it would pass through the x-axis. And since there are no other zeros, it can't pass through the x-axis. It has to look like that. And so that is our graph. Now, if you don't believe me, we can look at our graphing calculator, x to the fourth minus x squared minus 12, and then x to the third minus 27. And we see when I look at and I hit the graph, we see that we get a shape that's very similar to what I had there. Well, I think we'll only do these two examples for today. That should get us through. And the Macaulay fun fact of the day is that Macaulay's first car ever was a 1985 Chevy Chevette. It was a little 4-cylinder. It was a stick shift that had 4 gears. There was only vent and heat. There was no air conditioning in it. And the radio had 1 speaker that was right about there. And you can see there was just an itty bitty little accelerator button, and it was a great car, and I miss it dearly. That's all I got for today, folks. Have a good day. Bye.